Hi, welcome back. This is Albert. In the last video, we already know what the non-design domain is. In this video, we will take a very simple museum design as an example. This museum was also used as an example in the Ameba animation. It has a curved roof. A spiral ramp is designed from the ground to the roof. I believe this example will help us further understand the concept of the non-design domain. To save your time, you can directly visit the GitHub link in the introduction of this video to download the initial design domain of this example. If you would like to learn about its modeling process, you can drag your progress bar to the end of the video. Now, let's start the topology optimization part of this example. The first step, the initial design, is a closed B-wrap, so we need to pick the non-design domain surfaces. Those are the roof and the spiral ramp, here and here. They have to be defined as non-design domains because they will be applied uniformly distributed loads. So we can pick them into Grasshopper. The first one is the roof. The second one is the spiral ramp. Okay. So here we will have these two model, and we can rename them. For example, this is the roof. This is the ramp. Okay. Okay, we have already got about 1.2 million elements. This is a very large number. As you can see, the mesh has already divided. The next step, we need to define loading and boundary conditions. We can hide it at the moment. And okay, let me remove the grid. Okay, as you can see that in this model, we already have four squares here. They are supports. We can define supports first. Support is 3D surface, and we can connect the G button, maybe G port, maybe called, and click this select button to pick here. I suggest you to click the boundary of this surface. That would be easier to pick them. Like this, 3, 4. Okay, they are all supports, and right click, and we may give them a 0 to limit their displacement. And next we can define the load. The load should be 3D surface load. Yeah. To be simplified, we can use the same number to the roof and the ramp, so we can join input G. We can give the roof first, maybe Z. We can give the -1 here. For the ramp, we can copy again and pick the here. Oh, we may need to pick them one by one. Okay, so they are loads. Before we continue, we need to also define a non-design domain here, because we want to keep these elements. So we can directly create a box. Create a box here, maybe use this 3 point here. We want to keep these elements, and they are also the non-design domain. Okay, after we have already defined load and the supports, we can define the non-design domain. That is, we can use this component. This is in mesh. It can help us to select the finite elements. For example, all of elements in this non-design domain brep can be selected as non-design domain elements. So we can connect G first, and use here is mesh. We can convert all of the elements, all of brep into mesh, like this. And the roof, currently the roof is it's just a surface, and the ramp is also a surface. So we may need to convert them into a closed brep. So we can use maybe Z and give the extrude surface, extrude, and the size maybe minus 12, because the size of elements is 6. Here is 6, so we can use 12. And we can copy one and remove them, connect them together. Okay, so we have 2 meshes here. All of the elements in this can be selected. We can use 3. We can use 3. So as you can see, the elements index has already been selected. So the next step, we can define using a non-design domain and input their element index. This. So the next step, we can collect all of these conditions together. We can use multiple load keys and to connect with the support, and then we can use pre-processing. Use G here and connect the multiple load keys and non-design domain. Okay, in this way we have already defined the loading and boundary condition and the non-design domains. We can start to do topology optimization. We can use the solver here and use the display to connect the G and connect the steps. Next, we still need to adjust the parameters. For example, we can move target volume into 25, and the filter radius should be 18 because we use 6 as the mesh size. And other thing is fine, and we don't need to adjust them. Maybe volume target we can give the 20%. Okay. So we can open the window. So I'm in Australia, so we can use Australia server. If you are in US, you can use the US one, and click start. Okay, after 91 iteration steps, the optimization has converged. Let's look at the result. Let's hide all of these components first and the initial design domain. If you cannot see the structure clear, you can use this render display and connect the mesh. I think the result looks good, and as you can see that there's some rendering errors that is caused by non-manifold features, as we have already mentioned before. If you think this result is good enough, you can bake the mesh. And then, as you can see that the model has a lot of rendering errors. This is because the non-manifold features, as we mentioned before. So, in this tutorial, we will use a very simple and commonly used method to fix this problem. In this case, we will use Reno 8. Reno 8 has a very powerful function that is called shrink wrap. So we can launch the Reno 8 first. Okay, after you have already launched the Reno 8, you can copy the model in Reno 7 to Reno 8. Okay, so here you will have the mesh model in Reno 8. You can use the shrink wrap function, and we can use the target. We can change the target edge length. The mesh size is 6 millimeter. We can use maybe 5 or 4 here, and we can give the smoothing iteration, and other parameters can we don't need to adjust them. Okay, so as you can see that the model has already been fixed, but the topology looks a little bit weird. We can further improve this, but currently the result is already a little bit good, and we may use the next function that is called remesh to adjust the topology. Maybe we can use 6000. Okay, as you can see, the code remesh function makes the topology perfect, and everything is good now. So we can copy paste to Reno 7, and we can set a rendering mode, maybe Arctic. Yeah, this will be the result of this tutorial. I think it's good.